So what we're going to look at now is we're going to look at something called the mean value theorem. And the mean value theorem is a very powerful application of calculus. All right. And in particular, it's a very powerful application of that whole idea of the maximums and minimums that we've been using throughout the course. Okay. And so what we'll do is we're going to start out with what's called a corollary of the mean value theorem, which is called Rolle's theorem. And so when we talk about the corollary, it's like a softer version, or it's like something that can be used in addition to the mean value theorem. And so you'll see the point once we go through both Rolle's theorem and the mean value theorem. So first, with Rolle's theorem, let's f be a function that satisfies these following three hypotheses. Okay, and so we're going to do some proving work here. All right, so notice what the hypotheses are. F is continuous on the closed interval a to b. F is differentiable on the open interval a to b. So that means it doesn't have to be differentiable at a or b. Okay, and f of a equals f of b. All right, so basically at the endpoints, all right, the endpoints are equal to each other. Then there is a number c in a to b such that f prime of c equals 0. Okay, notice again we use this a number, not one number, a number. It could be multiples. Okay, so let's take a look at some examples. Let's say, for example, this is a and this is b. Okay, and so here we'll make this be f of a, and we're told that f of b is also the same. So if we think about it, what can happen since f is continuous? So f is continuous on this closed interval. So basically, it's got to look something like this, say, for example. Okay? All right? Now, if it looks like that, then what we have is right here at this at the relative minimum, we have f prime of c equal to 0. Right? Proves it. Totally true. Let's take a look at another one. Let's say, for example, a to b. All right? But instead of going downward, all right, we're going to have the function go upward. Okay, let's say it does one of these things. Okay, well then, f prime of 0, or f prime of c is going to equal 0 at this point. Okay, that'll be our c. Right, just like here, this one here was our c. Another option is that we actually have multiple points in which this is true. All right. And so like if we do something along those lines, just a little bit clearer. So now at this point here, we call this one, we might call that one C1. We'll call this C2. We'll call this C3. So there's actually now 3 places where f prime of C is equal to 0. And then finally, we might have this other option. Okay, and here's A, here's B, and in this case, all we have is actually a horizontal line. So in this case, f prime of c equals 0 for all c belonging to A to B. And so what you can kind of see here with Rolle's theorem, the whole idea of Rolle's theorem is that if I have 2 endpoints, right, if I begin and end at the same place, okay, no matter what direction I go in, if I go up, I go down, whatever it is, I have to hit the very tippy top point, okay, and then come back down, right? Okay, so I've got to hit a maximum and then turn it into another direction and go the other way. Or I've got to hit a minimum and go the other way. Or I can hit multiple maximums and minimums, or I don't go anywhere, but then in that case, I've got a horizontal line, so the derivative is 0 everywhere along that line. Okay, and that's the idea behind Rolle's theorem. Okay, if I've got a continuous function, right, no breaks in it, f is differentiable everywhere, and I'm starting and ending at the same point, right, at the same y value, then somewhere I've got to hit a max or a min. I've got to turn around, essentially. So how do we use this? Well, let's take a look, right? It's basically a proof, and all it is showing existence. So what we want to do, let's say we want to verify that the function satisfies the 3 hypotheses of Rolle's theorem on the given interval, then find all the numbers c that satisfy the conclusion. All right, so if we use Rolle's theorem, first we want to confirm continuity. So that's our continuity requirement. And so since f is a polynomial, right? And we know that polynomials are continuous everywhere, then f is continuous on 0 to 3. 2, differentiability. Again, since f is a polynomial, f is differentiable everywhere. Polynomials are like that. Not every function's like this, but polynomials are. Okay, f is differentiable everywhere. Then 3, we have the requirement that f of a equals f of b. So I'm going to have to actually test that. Okay, so actually f is differentiable. I should add this piece. F is differentiable on 0 to 3, the open interval, right? Because that's the requirement. Continuous on the closed interval, differentiable on the open one. Well, let's check. F of 0, so that's our endpoint, is going to equal 0 minus 0 minus 0 plus 2, which equals 2. Then f of 3 is going to equal, right, 3 cubed is 27, minus 3 squared is 9, minus 18 plus 2, and that is also going to equal 2. So now we've got the 3 conditions of Rolle's theorem confirmed. So what this means is there exists as a result a value c belonging to 0 to 3 such that f prime of c equals 0. So now we know that that actually is true. In this case, it's not going to be so hard because basically all we're going to need to do is take the derivative and then show that in fact there is one in there. We'll find the one, okay? But the whole idea here is that what if it wasn't so easy? What if it wasn't so simple to find where the derivative equals 0? Well, now all I need to do is use these 3 rules, okay? These 3, call them requirements: continuity, differentiability on the open interval, and f of a equaling f of b, and then I can show that f prime of c is going to, in fact, equal 0. So now what I'm going to do is I'm going to find those values where I'm going to find the values of c. So f prime of c, or f prime of x, excuse me, is going to equal 3x squared minus 2x minus 6, okay? Then we're going to set that equal to 0. 3x squared minus 2x minus 6 equals 0, okay, just like we were doing before. I'll use the quadratic to solve this one. So we have, and the nice thing is that I actually, in fact, know that this is going to, in fact, give me a value. So x is going to equal 2 plus or minus the square root of 4 minus 4 times 3 times negative 6, all over 2 times 3. So this is going to give me 2, and this is 4 minus 12, so 4 plus 72, so this is going to be plus or minus the square root of 76 divided by 6. And I do know that the square root of 76 is going to be divisible by 4. So that is 19. Okay, so this is going to be 2 plus or minus 2 root 19 over 6. Excuse me, 2 root 19 over 6. And this is thus going to end up equaling, okay, 1 plus or minus the square root of 19 divided by 6. Okay. Now, if I think about it, you can go in and check on your calculator, but I'll tell you that this is going to end up being our plus the square root of 17 minus the square root of 17 is going to be negative, and the interval that we're looking for is 0 to 3. So c equals 1 plus the square root of 17 divided by 6. And that's our answer. All right, just like we were doing with maxes and mins, take the derivative, set it equal to 0, and then solve. Now let's look at the mean value theorem. The mean value theorem is very similar to Rolle's theorem. It's what's called the generalization of Rolle's theorem. What we're going to get with the mean value theorem is we're just going to get a very different kind of interpretation. So if we let f be a function that satisfies the following hypotheses, f is continuous on the closed interval a to b, f is differentiable on the open interval a to b, but we're not going to have that third requirement. No third requirement for f of a equals f of b. Then there is a number c in a to b such that f prime of c equals f of b minus f of a. So let's look at what this means kind of graphically. So let's say, for example, I have a here and I have b here, and I'm going to have f of a, okay, and I'm going to have f of b. All right. Now, what this is saying is that I want to imagine that I've got a line that goes through a to b. Okay, it goes through a to b. It's a straight line, goes through a to b. All right. The slope of this line is the average, also called the mean, of all of the derivatives between, okay, a and b. For all those derivatives between a and b, okay, so you take the derivative of every point along that line, the average value of all of those derivatives is in fact this straight line, okay? Now, why it ends up with that there's a number of c such that f prime of c is equal to f of b minus f of a over b minus a is that somewhere, let's imagine that we draw, I'll put this now in red. We draw a picture, okay? We do something like this, okay? Right? Now that's continuous everywhere, continuous and differentiable. And what you're going to get is that somewhere, right? Say, for example, like we can kind of see it maybe right about here, okay? Right about there, we're going to have some value c. This is going to be our value c, all right? Such that the slope of the tangent line to the graph is equal to the slope of our mean value graph, okay? Or we might look at something like right about here as well, same idea, same principle, okay? There's another one, right? Where the slope of that tangent line is equal to the slope of our line on the mean value, for the mean value theorem. Or another one here, this one kind of looks like it too. So those all have basically the same slope, right? Okay, and they have the slope that's equal to f of b minus f of a over b minus a. Okay, that's the slope of this line that is stretched between a to b. And so that's kind of the idea that we're working with here when we work with the mean value theorem. We're saying, you know what? I don't know what that value is, but I do know it exists as long as I have f is continuous and f is differentiable in the open interval. Okay, it's got to have somewhere in that interval where the slope of the tangent line to the function is equal to the slope of the line between the 2 points a and b. So let's verify that the function satisfies the hypotheses of the mean value theorem on the given interval, and then find the number c that satisfy the conclusion. Okay, so what we're going to do is we're going to do two things, right? Now, for the mean value theorem, I only have two requirements, right? One is my continuity requirement. And so since f is a polynomial, f is continuous on -2 to 2. And then 2, we have differentiability. I'm just going to call that diff, right? Since f, again, is a polynomial, f is differentiable on -2 to 2, right? Because it's actually differentiable everywhere. And this is, in fact, our open interval this time, not a closed one, open interval, -2 to 2. So, by the mean value theorem, okay, and you've got to write this too, by the way. By the mean value theorem, there exists a c belonging to, right, -2 to 2 let's actually put our c down here, c belonging to negative 2 to 2, such that, okay, f prime of c equals, and this would be f of negative 2 minus f of 2 over, or excuse me, let's do the endpoint. F of 2 minus f of negative 2 divided by 2 minus a negative 2. Okay, and so that's the difference in the y's over the difference in the x's. So doing a little calculation, what we end up with is we get 4 minus 0 divided by 4, or equals 1. Okay, so that's actually the slope of that line that we generated from going from A to B. So now all I've got to do is show that the derivative, okay, so here's step 2, right? Part 2 is we want to show, right, we want to find an f prime of c equal to 1. So f prime of x is going to equal 3x squared minus 3. So we set that equal to 1. 3x squared minus 3 equals 1. Equals 1. And so that means that 3x squared is going to end up equaling 4. So x squared will equal 4 over 3. And so x will equal this plus or minus the square root of 4 over 3. Okay, which is going to be plus or minus 2 over root 3, which is equal to 2 root 3 over 3, plus or minus. Now, what we need now is we need to notice that because we're only looking from negative 2 to 2, so which one's actually in there, all right? Or is it both of them? Because it could be both of them. So we'll go and we'll check. Now, x ends up equaling basically plus or minus 1.732, okay? So both are our c's. So those are both of the c's that we're looking for, right? Both positive and negative 1.732, right? Those are all the numbers c that satisfy our conditions, where the slope or the derivative ends up equaling the slope of the line stretched between negative 2 and 2. Okay, and that's how we use the mean value theorem, right? It's a proof. So we want to show the two requirements of the proof are fulfilled, and then we just make the statement, right, that by the mean value theorem, we have an f prime of c that will give us this particular slope, right? We don't know what it is yet, but we know that it does exist. Okay.